Alright, so our learning target is 2.5. We're going to use electron configurations to determine the number of valence electrons and draw a Lewis structure. So you're going to have to determine valence electrons from the electron configuration, draw the Lewis structure, and determine the family that an element is in based on its Lewis structure. Alright, so a Lewis structure is going to represent valence electrons. Alright, the valence electrons are the electrons in the outermost energy level, so the ones furthest away from the nucleus. Those are important because those are the electrons that are most responsible for our atom behavior. Alright, now, you can have no more than 8 valence electrons. So if you have more than 8, you got to go back and fix it. Alright, so remember that we did the electron configurations for these elements in class. We can determine the number of valence electrons by looking at the electron configuration. So when we look at the electron configuration, this number right here is the energy level. Okay, so we look at the coefficient, and here 3 is the highest energy level, so sodium has 1 valence electron. If we look at sulfur, we have 3 in 2 places, the S and the P. So we have 2 plus 4 for a total of 6 valence electrons. For manganese, the highest energy level is 4. So we have 2 electrons there, so 4 valence electrons. For tin, we have 5 S2, and then we have 5 P2. 4 is a lower energy level. Okay, so the highest energy level is 5. So we have 2 in the S and 2 in the P for a total of 4 valence electrons. I just realized this was 2. Sorry about that. And then for barium, 6 is the highest energy level, so we have 2 valence electrons. Now there's a much simpler way to do this as well. If we look at our periodic table, we know there are patterns, alright? So we know that in the first column where there are S1s, there's 1 valence electron. The second column, there's 2. We skip the transition metals because those are all in transition. So in the boron family, there's 3. And then in the carbon family, there's 4. Nitrogen family is 5. Chalcogen family is 6. Halogen family is 7. And the noble gases are 8, except for helium. So if you just remember this pattern, you'll be able to determine number of valence electrons all the time. So here's the slide that goes through all of that. You can pause it and copy it if you like. So to write the dot diagram, you're going to write the symbol for the element, then surround it with the correct number of valence electrons. We're going to pair the first 2 electrons because those are our S electrons. Then we're going to occupy each side until we have to pair. These are our P electrons. So just like our orbital diagrams, we want to make sure we're putting in the correct order. So for sodium, the symbol is Na. We had 1 valence electron, so we put 1 dot on the symbol for sodium. For sulfur, remember we had 2 valence electrons in the S and then 4 in the P for a total of 6. So for sulfur, we say 1, 2 together for the S, then 3, 4, 5 because these are our P orbitals, and then the 6th one gets paired here. For manganese, we had 2 valence electrons, so we put both of those together to represent the S. For tin, we had 4. So 1, 2 together, then 3 and 4. For barium, we had 2 valence electrons, so we put 1 and 2. So let's talk just a minute about why the valence electrons are important again. Stability is the ultimate goal of everything in the universe. All right, everything wants to become stable, and this is what drives all behavior. So the octet rule tells us that 8 valence electrons make an element stable because that completes the outer energy level. That makes the S and the P sublevels full, and full means they're stable. Alright, so the atoms want to achieve a noble gas electron configuration because those are the most stable atoms. The noble gases don't tend to react with anything. And this is what we call isoelectronic. That prefix iso means the same. So isoelectronic means they have the same electron configuration. So how does that happen? Well, for example, let's look at sodium. This is its electron configuration, so neon 3s1. So sodium has one valence electron. If it loses that one valence electron, then it becomes just like neon in terms of electrons. Okay, so it loses 3s1 and it becomes just like neon, and we call it Na+1 because now it has 11 protons, but it only has 10 electrons, so it has a +1 charge. So it's isoelectronic with neon. It has the same number of electrons. And these are what we call ions, and we'll be talking a lot more about them coming up. So oxygen, its electron configuration is 2s2, 2p4. So it has 6 valence electrons. It only needs 2 more to have this p sublevel complete so that its S and its P would be full. So it gains 2 more electrons, all right, and because it has 2 more electrons, that means it has a total of 10. Compare that to 8 protons and 10 electrons, we get a -2 charge. So it's isoelectronic with neon. So this sodium ion is isoelectronic with the oxide ion, and those are isoelectronic with neon. Some exceptions, full or half-full sublevel. And this usually happens in transition metals. So those things will rearrange their sublevels. So like chromium, it only needs 1 more electron to have 5d orbitals. 5d electrons, so each orbital would be occupied. So it borrows from the 4s2 because that's a lower energy level. So it ends up looking like this, 4s1, 3d5, and you may see that on some of your printed material. Same thing happens for copper. You only need 1 more electron to have a full d sublevel here, so it borrows it from 4s2. So for copper, you might see the electron configuration written like this. Now you don't have to memorize these or anything like that. Just know that this is why things happen the way they do.